Welcome. I'm Judah Levine. I'm in the faculty in the physics department here. I'd like to welcome you to the Saturday afternoon talks. We try to have them once a month, and keep an eye out for the next one. Today's speaker is Daniel Slichter. He's a physicist in the NIST Ion Storage Group. NIST is just down the road, if you don't know it. His research focuses on experimental techniques for quantum computing, quantum networking, and quantum sensing with trapped atomic ions in ultra-high vacuum. He received his PhD from the University of California, Berkeley in 2011 for research on quantum measurement in superconducting quantum circuits. Of course, quantum anything is a hot topic right now, so we look forward to his talk. Dan.
Great, thanks, Judah. Can everyone, all right. Thank me after I've told you something, yeah. Everybody hear me okay with this volume? I'm pretty loud, but yeah, okay. So my name's Daniel Slichter. As Judah mentioned, I have been doing quantum science in various degrees for about 20 years now. And I find it really fascinating, and I'm here to share with you a little bit about a particular topic, which is quantum computing. And there's been sort of a lot of hype and things in the news, and I just sort of give you a sense of like, well, what actually is it, and how far along actually are we on this journey? So there's lots of big quantum plans that lots of people have, and if you go online, you can find all sorts of graphic design money has been spent on making it sound good. So the question is, well, what's really going on? So, sort of maybe a baseline question is, what is quantum mechanics? And so if you ask the internet to have a picture, it's like nobody really knows how to draw quantum mechanics. It's something that's kind of mysterious and wavy, maybe. But basically, quantum mechanics is a set of mathematical rules that people have come up with to describe the behavior of systems that we see in the laboratory or in the world. And the things that obey these sorts of rules are either generally very small, like a single atom or a single particle of some sort, or they might be very cold, very close to absolute zero in temperature, or they might be very sort of isolated from everything else in the world, any other particles or things like that. These are not hard and fast rules, but this is sort of generally things that quantum mechanics pertains to. And what quantum computing is really, fundamentally, it is an attempt to make a large system that you can control in whatever ways you want to, that still obeys quantum mechanics. I mean, here we are, and none of us, as we experience the world, see quantum phenomena, really, in how we do things. And I'll talk about some of the weird phenomena of quantum mechanics later on in the talk, but basically, we don't see that because once you get away from these small, cold, isolated scales, basically quantum mechanics ends up sort of averaging out, and the way it averages out effectively looks like this sort of classical world that we know. So quantum computing is really an opportunity to sort of say, how big can we make a quantum thing? How well can we control this? How exotic a quantum state can we prepare? What would it be useful for? One use is there are very specific types of hard computational problems that a quantum computer might be good at. We believe mathematically would be good at. Another thing it might be really good at, I think this is sort of the main use that I find compelling, is that would let you simulate and understand more about naturally occurring complex quantum systems. Like some exotic material has some kind of behavior. We don't know why it has that behavior. And the sort of mathematical models that we have that tell us about how some kind of materials work don't really work for other materials. It's too complicated to try and calculate it. But if you had a quantum computer, maybe you could calculate these sorts of things. So let's start first, slowly. I'm going to talk about what I call classical computing, and what classical means is just not quantum. So non-quantum computing uses what we call bits. And a bit is just a system that has two possible states. It's a switch, right? Here's a simple switch. It's on or it's off. This is a bit, right? And when you have digital information, it is encoded and it's processed as a series of bits. And so you might have a string of bits like this, and these might represent some characters in an email that you've typed. They might be some pixel colors in an image that you've taken. Any kind of information that you process or work on with computers is encoded as bits. They're different physical forms of bits. So for example, in a processor, the bit might be represented by a transistor that has a voltage on it that's high or low. But it could also, on a hard drive, and these are getting phased out, but it might be a little magnetic domain on a hard drive that's up or down, right? But you might also not really think about, a bit is also a pulse of light in an optical fiber. And any of you who uses the internet ever, you use a lot of these bits. Eventually, the light is on or off. Or it could be a Wi-Fi signal of some sort, and the signal being on or off. These are simplifications of how they encode bits in these things. But the idea is basically we use billions or trillions of these classical bits all the time in these different physical forms. So now I'm going to tell you about quantum bits, or qubits for short. And a quantum bit is just a quantum system, a system that obeys the laws of quantum mechanics that has two possible quantum states. So sort of the canonical qubit is a little electron spin. You can think of an electron as being like a little bar magnet. And the little bar magnet can either point up or point down. And there are sort of two states associated with the spin pointing up or the spin pointing down. But you can also encode a qubit into a system that has more than two states, as long as you can pick two and sort of isolate them. So for example, an atom has multiple states, but you could pick these two and say, I'm going to make those two my two quantum states that I make a qubit. You can also do something that's not as tiny. You can do something that's kind of macroscopic. This is a superconducting circuit that I made in my PhD. And this is sort of the diameter of like a red blood cell, in here or something like that. So it's kind of big, actually, compared to a single atom. But this also has energy levels, if you cool it down cold enough, that you can address as individual quantum levels. You can also use a photon, which is a particle of light, and you can encode quantum information in that. And so basically, just as with classical bits, there's many ways that we make classical bits. There's also many possible ways you could make a quantum bit. And they all have their different pros and cons. And if you get people who work on these things together and give them enough beer, they will argue till the morning about it. But anyway, I think they're all fun. So now we have to start talking about some funny features of quantum mechanics. And so I'm going to introduce the concept of superposition, quantum superposition here. And I'm going to make a little bit of notational remark here. So we've got this symbol here. This is a Greek letter psi. And then we've got this little vertical bar and this little angly thing around it. And basically, anything that's inside between the vertical bar and the angly thing, that's just a way that we denote a state that is a quantum state. So if you see something that's in that kind of thing, that just means quantum. We call that a ket, but it just means a quantum state. So here's our two states. And so we could say for this quantum bit here, let's say its state is 0. We'll call that off. And its state is 1. We'll call that on, right? OK, so this is just like a switch, on or off. But then we get this other weird thing that happens in quantum mechanics, but not in regular switches. And that is you can have a state that looks like this, which is kind of both off and on at the same time in some sense. This is weird. This doesn't make intuitive sense to us based on our understanding of the world. But as far as we can tell, we can write down math that represents how atoms and electrons behave, and you kind of have to consider their having this nature here. And we call A and B here the amplitudes, the quantum amplitudes. And so superposition is just this statement that this qubit can be both on and off at the same time. And so then now I'm going to talk about what happens when you take a quantum system and you measure it. You try and see what's going on. So let's take our qubit and we'll hook it up to some kind of a meter. And I'm going to sketch this out generically. I can tell you in all sorts of detail how we actually do this sort of thing in the lab with different technologies later on. So the meter will either show you a big 0 or a big 1. This is something that's like in the lab you can actually put your hands on and see it's like a big thing. It's not an atom. And so when you're in the qubit state 1, the meter will read 1. And when you're in the qubit state 0, the meter will read 0, right? OK, so this is nice. And there's actually a coupling back and forth between the qubit and the meter. Because the question is, what happens if you have this state right here? Right? What happens if you're in this superposition where you're sort of both 0 and 1 at the same time? Well, the meter only reads one thing. What happens is it might read 0, it might read 1, and actually what happens is if you put this state in and couple it to the meter with some probability, which is given by the square of this amplitude, the meter will read 1, and actually the qubit state will change to be 1. It will no longer be its superposition state. It will be changed by the measurement. Just by looking at this qubit, you have changed what state it's in. And then with this probability, the meter reads 0, and the state changes to be 0. And so if you do a thing with the qubit where you say, OK, I did this. I got a result, right? I measured 0 or 1. And then you say, I'm going to go back. I'm going to make the same. I'm going to re-prepare this same quantum state over again. Get back to this state. And then measure it again, and then re-prepare, and then measure it again. And you do this many, many, many times. You'll find that the probabilities, the number of times the meter read 1 is b squared, and the number of times the probability the meter reads 0 is a squared. But in any single shot, it's just one or the other. So basically, and so this tells you something about the quantum amplitudes have to sum to 1 because the probabilities have to sum to 1. But so basically, the act of measuring a quantum system changes the state of the qubit, and we call this projection. And it will destroy any superposition that you have, any of this sort of magical stuff that's going on, this bothness. So you can kind of imagine, if just looking at something changes it, that's something that's pretty fragile. No wonder, we don't see as much of this in our everyday experience. So let's get a little bit fancy, all right? We can talk about more than one bit, right? So if we have more than one bit, you've got 2 bits, and there's 4 possibilities that those bits can be in. They can each be in 0 or 1. If you add a 3rd bit, now there's 8 possibilities they can be in. They can each be in 0 or 1, and so on and so forth. And so if you have n classical bits like this, there are actually 2 to the n possible combinations of 0 and 1 that they can be in. But they can only be in 1 at any given time, right? The switches are all either just on or off. So now I'm going to talk about, and I've got this slide out of order, so I'm going to talk about, with superposition, quantum interference that can happen when you have a state that's in superposition. So now, I'm sorry, I had this slide one before. I should have done it. Anyway, so that's what you get for finishing your talk right now. So here is a classic quantum experiment where you take some quantum particles and you shoot them in such a way that they can pass through one or the other of 2 little skinny slits, and then they land against a screen here where you see where they've landed. And what happens is, if you say block one of these slits, or you block the other one of these slits so that there's only one path that the particle can go through, you get something that looks like this, where sort of you either get, if slit 2 is open, right, then you kind of get a big hump in front of slit 2. And if slit 1 is open, you get sort of a big hump in front of slit 1. So this is nice. But then if you open both slits, now you have sort of a superposition. You're going through both 1 and 2 at the same time. And what happens is, it doesn't look like this one plus that one. There's these extra strange wiggles in here. And it comes because these quantum states that are in superposition, the quantum amplitudes that are associated with them can interfere with each other. They basically add and subtract like waves and change their amplitudes. And so this is another sort of key feature of quantum mechanics that we have to understand. So there's this superposition. You can get this interference. Now, I would just want to say, if you don't understand what's going on, I didn't understand it when I took quantum mechanics in college either. It was just like, this makes no sense to me. You just kind of have to suspend disbelief and go with it. And I've been doing this for 20 years now, so I sort of work easily with it. But if it doesn't make sense to you, that's right. Okay, so yeah. So anyway, so we get this sort of quantum interference. So anyway, so I'll go back quickly to remind that here we are with, if we have more than one classical bit, we have 2 to the n possible combinations that the classical bit can be in, but you're only going to be in any one of them at any given time, right? The switches have some configuration. So now, what happens if we get even fancier and we have more than one qubit, right? Now let's say we've got 2 qubits. So there's 4 possibilities that these 2 qubits can be in together. But let's say that qubit A is in some superposition state like this, right? And then let's say that qubit B is in the state 0. Well, what's the combined state of these two together? Well, it turns out you can write it down like this. And this is a superposition state where you're in more than one state at the same time, right? So we're more than one state at the same time. We can believe that. But all right, now if this one's in superposition and the second one is in superposition, now you can be in all 4 of the possibilities at the same time. So unlike with classical bits, where you can only be in one combination at the same time, with quantum bits, you can be in more than one, up to all of the possible combinations at once at the same time. So superposition, you get sort of an exponentially large number of states once you have a certain number of qubits, that you can be in all of those states at the same time in some sense, if you're not measuring, if you're just leaving it alone to sort of do its quiet thing, right? So, is everybody following along now? Everybody's thoroughly bamboozled. All right, now we're going to really go down the rabbit hole. Okay, so now I'm going to talk about entanglement, which is another really essentially fundamental quantum phenomenon. So let's say you got 2 qubits, right? And they can be in one of these 2 states, and there's these 4 possibilities. Now I'm going to write down this state. So I want you to look at this state and tell me if you can write that as something which is qubit A is in a certain state times qubit B is in a certain state. And you can take a second and think about it, but really what you'll find is that you actually can't do that. This is a state that you can write down and that actually you can make in the laboratory where you can't think of it. You're not able to separate qubit A and qubit B out from each other in some way. They are entangled. You know, they're sort of like all twisted up with each other. You can't just kind of say, okay, we're going to tease you apart and, you know, there's some fundamental like knot that's got them together. And so now, what happens if you have an entangled state like this and you measure qubit A? Right? So if you measure qubit A, right, there's some 50% chance you'll get a 0 and a 50% chance you'll get a 1 because these amplitudes are the same here. All right, so you know this is like what we were saying before, right? You measure the superposition, and there's some chance you get this state, some chance you get that state. But now what happens after you've done that measurement? This is now projected from this state into 0, 0. So now if you measure qubit B, you're always going to measure 0. So it's not chancy anymore about qubit B. And if you measure 1, then you've projected this state into 1, 1. And now if you measure qubit B, you will always measure 1 again. This is also really, really bizarre. So these two systems are correlated with each other, and you can see it if you perform measurement. So I'm going to make a little example here. This is sort of a toy illustration that you could think about that maybe sort of helps you think about what's going on. So let's say we've got entangled dice, right? So what I've made here is a quantum state of 2 dice in an entangled state of all doubles, right? So this state is 1s, 2s, you know, snake eyes, double 2s, double 3s, double 4, double 5, double 6s, right? And these are all your options that you can be in. And so I say, all right, so you take a die, you put it in a dice cup so you can't see it, you shake it, and you give the other one to your friend or whoever you want to give it to, and they take it and they shake it. Maybe they go in another room, right? So you go and you roll your dice, right? And you see what you get. You got a 5, right? Then your friend comes back in the other room and you ask them, what'd you get? And they're like, I got a 5, right? And you're like, okay, this is kind of weird. So now, all right, let's re-prepare our entangled dice state again, all right? So now, okay, now you take your dice and you shake it up and you say, what'd I get? I got a 3. And your friend comes in from the other room and they're like, well, I got a 3 also, right? And then you do it again. And this time you roll a 2. And your friend rolls a 2. And you do it again, and then you both get 3s, right? So this is really, really, if you look at just your dice, right, what's going on here, you can keep doing this all day. Your rolls, this just looks random, right? It just looks random, like a normal dice to you. But your friend always rolls the same thing that you're rolling. They are always correlated with what you're rolling. This is so weird. This is not like anything that we experience in our everyday lives. But this is the reality of quantum mechanics. And this disturbed a lot of people who are very serious physicists over the years. And people have done a number of tests to be like, no, well, this can't be true. There must be some hidden underlying truth that makes it so that this is not the case. And people have done a number of experiments over the years, including some really beautiful experiments at NIST right down the road, and in other places using NIST technology that have demonstrated that, in fact, this is what it is. And in fact, you can take your die and your friend's die, and you can both get in spaceships and go to opposite sides of the universe and roll your die once you get there. And then you journey back, and you will find that, yes, you rolled the same thing, even though there was no way that they could have signaled to each other from across the universe. Yeah?
Quick question. If your friend rolls first,
uh-huh.
do you follow him exactly?
Yes, I mean, yeah. So it doesn't matter which one goes first. And I mean, this is a little bit of a constructed example. But yes, the idea is it doesn't matter which one goes first, but the other one will always follow suit then. So this is really, really strange, but it can be really powerful. So now let's talk about computing. Let's talk about sort of classical or non-quantum computing. So here's a picture of some piece of a motherboard, and you see all these little chips here. And they look like something that you can't see inside, and there's some wires that come in and some wires that come out, right? So I'm going to draw that, right? This is what some computer chip looks like. There's some wires that come in, and there's some n bits of input that you've got. And then there's some wires that come out, and there's sort of m bits of output that come out. And inside, what's going on? Inside, there are what we call universal logical gates. And these allow you to perform logical operations. So this bit and this bit, are they the same? Are they different? You can say a logical and or a logical or a logical not on these. And this actually allows you to do everything that goes on in your phone, your computer, or whatever is sort of built up out of primitives like this at the very base level. This allows you to do arbitrary computations that you want to do. And then if you want to test what this circuit does, if you don't know, if you got a mystery thing in here, and you know what it does, you just test all the inputs by just running it 2 to the n times on all the possible inputs, which could be slow if you have a lot of inputs, right? So yeah, all right. Now, what does a quantum computer look like? A quantum computer, you have n qubits, and you have n qubits that come in. And then inside, there's a universal quantum gate set that gives you your desired algorithm. So what does a universal quantum gate set look like? So the building blocks of a quantum algorithm are what we call quantum gates. A gate just means like a logical operation. And roughly speaking, you can do, and this is, again, very hand-wavy, but you can do operations on a single qubit, and those generally are used to create superposition, right? And then you can do operations on more than one qubit at a time, and those are used to create entanglement between qubits, right? And then can also be used to cause interference between qubits. And so quantum algorithms, what's going on inside is basically you are creating and manipulating superposition and entanglement and causing interference between all these quantum amplitudes for many different qubits at once. You're sort of making them do a very carefully calibrated artificial dance of some sort. So how this actually looks like is you have some sort of pulsed control signal that you apply to a qubit. It could be a laser, it could be a microwave field, it could be an electric field, it could be a magnetic field, it could be a gradient of one of these things. And here's an example from a friend of mine sort of shortly after PhD work, where basically this is a signal and it wiggles up and down for a period of time, and then you wiggle another signal, and then you wiggle these other signals, and all of this together makes an entangling operation, right? But so you can see there's very specific timing that you have to have, and these pulses have to have a certain shape and a certain amplitude and everything like that. And what's more, in a quantum computer, you need to be able to get these pulses to all of the qubits inside your quantum computer and be able to control them all in the ways that you want to. So that can be kind of tricky. So this is a drawing of what we call a quantum circuit, which is another word for sort of an algorithm. It looks a little bit like musical notation. These lines going across here, each one represents a qubit, and sort of going this way is like time, right? So this is a qubit going forward in time. And so you have a circuit here that has a certain width, which is the number of qubits that you have, and then it has a depth, which is the number of gates operations that you're doing. And what you're seeing here, these things that connect to 2, this is where you're doing some entangling operation between 2 qubits. And then these single ones here, this is where you're doing a single qubit sort of superposition type operation on 1 qubit. And so any sort of quantum algorithm relies on building up these sorts of single and 2 qubit operations to do some larger task that you want to do. So this quantum computer, we've got this universal gate set. It's doing our algorithm. And then what you would say is like, all right, if I want to try all the possible inputs, I just put this thing in a superposition state of all 2 to the n states at once, right? And then I just put it in and it just goes, right? I mean, that would be pretty cool, right? But the problem is, at the end of the day, you have to measure your quantum system. And when you measure it, you're stuck with this meter again. And the meter only says 1 or 0. It doesn't give you this nice superposition thing. So what you get out are n classical bits of information instead of 2 to the n classical bits of information. So there's this huge information bottleneck between what's going on in here and what you get to see at the output. And so this is kind of one of the big catches. Not only do you get only n bits of output, they're chosen randomly by nature. And so you need some clever algorithm to make it so that the output that you're interested in learning comes with more than just random chance probability. And you do that by exploiting quantum interference in here. And quantum interference, in the same way with those double slits, it makes some things sort of more probable and some things less probable. You use quantum interference in this algorithm to make the answers you're looking for more probable to measure at the end, and the answers you don't want to know less probable to measure at the end. There's a second catch, which is that this whole thing, all inside here, is very sensitive to noise and imperfections and everything like that. So I'm going to make sort of an analogy. You know, we can think about a quantum computer as being like a little quantum choir. Look, here are adorable, shiny-faced little qubits here, and they're all singing a song, and there's some conductor who is performing, you know, having them all do their quantum gates together, right? So what we are doing is we are singing a very long, very complicated, very, very quiet song as a choir. The singers all have to be in tune. They all have to be on tempo. They all have to be able to hear each other singing. You know, so these are all the qubits. They all kind of have to be really good individually and be able to hear all of each other. The conductor, the gates, they need to be able to talk to each singer individually. Now you, now you, now you. And you have to talk to them perfectly. You have to tell them exactly the right timing and the right pitch. And so as you go to a bigger choir, and as you go to longer songs, there's a bigger chance that somebody is going to screw up somewhere, and it's not going to come out the way that you wanted it to, right? And you know, this is this lovely picture, but actually the reality is that they're doing this at a rock concert. Because there's all these other particles and atoms and fields that you're not controlling that are all going on around there, and they're having a blast, and they don't care that you're trying to sing this very quiet, very delicate song all by yourself with your few little qubits, right? And so the challenge is that not only is our conductor not perfect, and our singers aren't perfect, but this other band is really, really loud. And so this is the essence of why making a quantum computer is difficult. So, you know, there's a reason that macroscopic objects, like people-sized objects, don't have obvious quantum effects that you see. So if you remember the dice, right, as soon as you roll one of them, you get a random result, right? The other one gets projected into its state. And if you can't see both of the results on both of the dice, right, you've kind of lost some information. You didn't know there was a correlation there. It just looks like random soup to you, right? So if your quantum system, your qubits, get entangled with anything else in the world accidentally, then some of the information that you have kind of gets shared with those things as well, right? And eventually, if enough of your quantum information in your system becomes entangled with enough of the rest of the world, then on average, it just looks kind of random. So we're all made of particles that are behaving quantum mechanically. And they're all getting entangled with each other all the time, actually, but just in sort of very minor ways. And then, you know, when you actually can't keep track of every single thing that's going on inside you, it just ends up looking kind of random. And when quantum stuff looks just kind of random, instead of having these coherent and interference type effects, that produces the sorts of physics that we call classical physics. And so, the big question is, how can you make a whole bunch of quantum particles that you can talk to easily, because you're doing all these gates on the particles, but they don't talk to each other when you don't want them to, and they don't talk to anything else in the world when you don't want them to? This is challenging, right? This is the essence of what the problem is here. Now, the good news is there's something you can do about this, and so I'm going to tell you about decoherence and errors. So let's say you start out with this nice superposition state, and you were planning on just having it hum along in your quantum algorithm and remain itself until it's time to do the next gate on it, right? But some environmental coupling or noise or something like that comes in, and now you've changed your amplitudes, right? It messed up the quantum state that you had a little bit. Or let's say you started off with a state and you were going to do some gate operation on this, right? You're going to take this state and you were going to turn it into this nice, pretty superposition. You know just what you want to be, but you didn't do your pulses exactly right. And so now the state is not the state that you had planned for it to be, right? All of these are sort of errors. And we can generally call this decoherence. And decoherence is basically when you've lost quantum information in some way. And the question is, well, can we, in classical communications, classical computer, we use error correction all the time. We use all sorts of things that allow you to catch an error and make the information come back again. Can we do something with quantum error correction? One of the problems is you can't copy a quantum state. This is sort of a famous theorem that is called the no cloning theorem. That if you have a quantum state, you don't know what it is, you can't make 2 copies of it. Wouldn't it be nice if we could? But we can't. Thanks, Bill Wooters. And so let's say you've got a state like this, right? Some superposition state. You can't copy it. But one thing that you could do is to use redundancy. You can say, all right, I'm going to use 3 qubits to hold this quantum state so that I don't lose track of what A and B are and have them turn into some other values that aren't what I want them to be, right? So I'm going to say, all right, I'm going to triple bag these qubits. I'm going to encode this one in 3 qubits, A times 000 and B times 111, right? So now, if you flip one accidentally, right? So if that third bit gets flipped accidentally, you've got an error, then you can sort of do a majority vote. And you can say, well, okay, I do a majority vote. These 2 say it's 0, and these 2 say it's 1, so I believe them. This is A times 0 plus B times 1, right? All right. So that's nice. So let's see. Let's see. How do we check for a quantum error? Okay, so we've got this state here. Let's call our qubits 1, 2, and 3. And what happens if we check for this by measuring an individual qubit? Okay, so let's measure qubit 1, all right? So with probability A squared, we get 0, and probability B squared, we get 1. And now our state is gone. We've lost our superposition because we measured our quantum state and we projected. So if you measure this qubit here, right, this is an entangled state. This is like rolling our entangled dice. You rolled the dice, and you got a number, and then the other one got a number, and now they're just 000 or 111. You've lost your A and your B because you projected the quantum state, because you learned something about what quantum state that qubit was in. And when you learn something about what quantum state it's in, it forces it to be in that state. So this is the problem. If you just measure single qubits, like you would think you would just do, you change your quantum state. So that's not going to work for us. So a basic idea of quantum error correction is that you can instead do things like measuring pairs of these qubits, which we call the parity. So let's say, okay, parity for 1 and 2 is you basically ask, are qubit 1 and qubit 2 in the same state? Don't tell me what state they're in, but do they agree with each other? And how about qubit 2 and 3? And how about qubit 3 and 1? Do they agree with each other, or are they in disagreement? So let's see. So right now we say, yes, they all agree with each other. That's good. Now, if you measure these things, it doesn't actually project you out of 0, 0, 0 and 1, 1, 1, because you don't learn any information about whether it's in 0, 0, 0 or 1, 1, 1. You just said, are they matching or not? And so it actually leaves the state unchanged by measuring this sort of funky parity feature of the state rather than trying to measure 1 qubit at a time. So now what happens if we have an error, right? So here we've got an error, right? So let's ask these parity questions. So are qubit 1 and qubit 2 in the same state? Yes, they are here, and yes, they are here. What about 2 and 3? They are not. What about 1 and 3? They are not, right? So you can look at this. This is what we call an error syndrome. You can look at this and deduce that qubit 3, whatever it is, it flipped. So you didn't learn what qubit 3 was or what any of the qubits were, but you learned that qubit 3 flipped. So now you can say, well, let's flip it back. Let's flip it back, and this will correct our error without actually us knowing anything about the quantum state that we had encoded. So this is sort of a very kind of, strange workaround way of doing it, but it lets you get around this challenge of quantum measurement. So now, how are we going to make a large-scale quantum computer if we've got errors and noise? Well, we just do an error-correcting code, right? So, all right, so we take these qubits and we encode them in more, but these will have errors too. So let's take these qubits and let's make those ones out of more encoded qubits. But those will have errors too. So then we'll make those out of more encoded qubits. And pretty soon, this gets to the point that you realize, like, we're going to need a bigger boat. Like, this is a real challenge because you've got to have a whole bunch of physical qubits to sort of encode this one logical qubit in a safe way. So let's talk about if you had such a large-scale quantum computer, what you could do with it. So the sort of face that launched 1,000 ships in quantum computing is what's known as Shor's algorithm. And there's some cousins to this. And this is basically factoring. So the problem with factoring is, like, let's say that you have a number y, and it is the product of two prime numbers, p and q. So like 15 is 3 times 5, right? So in this problem, if you're given y, it's hard to find p and q. But if you have p and q, you can make y easily. You just multiply two numbers together. And so the fact that this is a very asymmetric problem, it's very easy to multiply two numbers. It's very hard to figure out the two prime factors of a number. This asymmetry is what underlies all public key encryption technologies that we use. So RSA, Diffie-Hellman key exchange, all of this kind of stuff is based on this asymmetry. And Shor's algorithm was basically developed in 1994. Peter Shor realized that he could find a way where you could get an exponentially faster algorithm for figuring out p and q given y versus a classical computer. So basically, this would allow you, in principle, to crack all public key encryption. And so this got certain people very excited. 3-letter agencies are all over this sort of a thing, right? And so this sort of launched the thing. There's another big algorithm that sort of came on early, which is Grover's algorithm, which is unordered search, right? So let's say you have n mailboxes, they're all closed, and only one of them has a letter in it, and the rest of them are empty. So how many times do you have to look in a mailbox before you find the letter? And classically, you will need sort of n over 2. You'll have to open half the mailboxes before you find the letter. But quantumly, you can look square root of n times sort of in all mailboxes at once in superposition and find where the letter is. So this is a quadratic speedup as opposed to an exponential speedup. The quadratic speedup, I will argue, is not really a valuable thing, but it's an interesting thing. It's kind of cool. The third thing that you could do with this, and again, this is what I find sort of most compelling, is simulating some quantum system. So taking some real thing, like what's going on inside a material, and understanding how that actually works. This becomes exponentially hard as the system size grows, because you're trying to keep track of all of the quantum amplitudes of all the quantum particles that are coupled together in this material. But if you have a quantum system to do that, it sort of naturally has all those exponentially many amplitudes with which to keep track of what's going on. And so it's sort of a very natural thing that you could do. My perspective, nobody has yet found any other compelling algorithm to do with a quantum computer from a standpoint of being useful. So let's talk about sort of the specs of a classical versus a quantum computer, just to kind of help you think about what might you do. So let's talk about clock speed, like what is the rate at which you do operations, right? And so all of your computers have so many gigahertz or whatever on the processor. You've seen all this stuff on the sticker or the spec sheet or whatever. That means they're doing billions of operations per second. A quantum computer will do thousands, tens of thousands, maybe 1 million rounds of operations per second. So it's way slower, right? How about the size of the input you can give it? I mean, if you've got a server farm, you give it as much input as you want, right? You just spread that out. With a quantum computer, like if you've got a huge, large-scale, fantasy, amazing, we hope for it someday, quantum computer, you got 1,000 bits of input, right? Right now, you might have 20. That's a really small amount of input. But what about sort of the internal memory during computation? If you take sort of the largest supercomputer, you've got some number of petabytes. This is quadrillions of bytes of memory. But the size of the memory is larger than the number of protons in the known universe in a quantum computer. So that's kind of hard to beat, right? So this is where the quantum computer is really going to win. And of course, the quantum computer costs a huge amount of money. Go buy GPU chips, go do Bitcoin mining, whatever you want to do. That stuff is very cheap now. There's a huge industry that has made it extremely inexpensive. This is an enormous engineering problem we haven't solved, and it costs a lot of money. So basically, the take home from this is there are only certain special kinds of problems for which a quantum computer is really a compelling thing to do. You need a small input. You need an algorithm that requires that small input to blow up into a huge, exponentially large mid-circuit memory requirement. And then you need quantum interference as part of that makes only specific outputs highly probable to measure when you get your randomly measured output at the end. So this is not a general purpose machine. There are certain things that it will do really well. You are not all going to replace your iPhones with Q phones, okay? So this is not coming. So what are different quantum platforms that people have? How do people actually realize qubits? I've been talking about qubits with these sort of abstract diagrams, but what do we actually have? So trapped ions, this is what I work in. These dots here, each little dot is actually an individual charged atom that's held in vacuum. And this is a little string of atoms that are all held in vacuum together. And you can sort of see each one, and you can actually control each one. You could use a neutral atom that's not charged. You can hold these in optical tweezers. Each one of these dots is a little atom. You can make a superconducting circuit. You can make an electrical circuit out of some material like aluminum or niobium and cool it down to a fraction of a degree above absolute zero. And if you do it all right, these will behave as qubits too. And you can actually, this is what I did my PhD work on. You can take little tiny atom-like defects in the middle of a piece of silicon. And they're sort of like atoms in vacuum, but they're in a semiconductor instead of in vacuum. Similar thing with NV centers in diamond. Or you can use photons, particles of light, as qubits. And these are sort of the major platforms that different people are using to study quantum information, quantum computing these days. So what's it going to take to actually make that sort of useful quantum computer that we talked about? You're going to have lots of qubits, right? So you need something like 10 to the 4 error-corrected logical qubits. And each logical qubit is going to be made from sort of 100 or 1,000 physical qubits. So now we're talking about like millions of physical qubits. So you saw those nice pictures there. Those are like tens. So we've got some work cut out for us. And then the circuit depth. So for n qubits, the Shor's algorithm goes as n cubed. So you'll need, if you have 1,000 qubits, you'll have, 1 billion gates that you have to run in order to run the algorithm. And you can trade that off for qubit count, but there's some other things to do. Those qubits have to maintain their coherence. Their entanglement and superposition has to be what you want it to be throughout the computation. And it's not just enough to have a lot of qubits. You also need the gates and the measurement to be really accurate too. So you want sort of errors that are apart in 10,000, 1 in 10,000 chance that you screw up each time you do a gate, let's say. And then you also, and I've doubled this bottom here, but basically you also need to be able to entangle the qubits with any other qubits. So you need to be able to connect a qubit that you want here with a qubit that's over there pretty easily. Like it's not sufficient for the qubit to just really talk to its nearest neighbors. You can do that, but it comes with a big cost. And so a lot of how these things pan out depend on which of these qubit technologies you choose. So just a little bit of a where are we now? There are toy algorithms that people have demonstrated that are not classically tractable. So here's 2 quantum systems. This is one by Google Quantum, which is basically the purchase of John Martinez's Santa Barbara lab. And then this is one at USTC in China with photons. These are all mirrors and things on top of giant optical posts. This is like a hand-built giant optical table of optics. It's really sort of an amazing tour de force that they did this. But these are brute force demonstrations. You're not going to take this and make it a million qubits like this. That's not going to work. And second of all, the algorithms that they ran had only one purpose, which is you can't solve them classically. You can't solve them without a quantum computer. They're not actually useful for like you're going to do something with them, like, you know, make a better stock pick or, you know, optimize your this or that. That they're just to say, hey, we made a quantum system that was so big and so protected from the other things that we could do something that was so complicated that you can't replicate it with a regular computer and calculate that. So that's kind of neat. So we can right now run arbitrary quantum algorithms of a modest size. And so there's this metric called quantum volume that if some of you are aficionados out there, you may have heard of, which is basically what is the largest square random circuit with n qubits and depth n that you can run. And our current record is 19 qubits and depth 19 down the road here at Quantinuum. So, you know, we've got some work to do. This can be easily simulated on a Raspberry Pi with Python. So this is, you know, this is you know, I don't in any way mean to undercut the incredible engineering and effort that goes into this, but it's also, from a commercial standpoint, it's not a thing that is useful now. So you need at least sort of 50 qubits and depth of equivalent size or better to really be classically intractable. So basically, no algorithms right now that are sort of commercially or scientifically relevant are better on a quantum computer than on, you know, simulating it on a classical computer. This may yet change, and we're hoping that it will change, but this is where we are now. So this is just sort of reality check, not saying, let's stop doing this. So anyway, and a lot of the ideas, people are thinking about quadratic speedups, and as I mentioned before, I don't think a quadratic speedup, you know, given those clock rates and the cost, is really going to be something that's compelling. Quantum error correction that we've been talking about, this is just starting to happen. This is very exciting right now, is that people are finally able to do things where you say, we want to make a logical qubit where we take a bunch of physical qubits and encode quantum information in that and have that stay coherent, maintain its stuff, you know, be less sensitive to the background rock concert than any of the individual members of the choir. And we're almost there. We're really, there are groups that are like just squeaking at the edge of this right now. So this is an exciting time for that. Second of all, we need to be able to say, now that we've encoded these qubits, now we've got to take these logic qubits and get them to talk to each other. And this is also something that is again, just starting to happen. So we've got a few minutes left, and I can tell you just a little bit more, and I think maybe what I'm going to do is effectively more of like a lab tour than anything else, which is sort of for trapped ions in particular, which is what I work in now, to just give you a flavor of what does it look like? What does it actually look like in the lab to be operating these qubits and trying to perform quantum algorithms. So basically, trapped ion qubits, you can use sort of the electronic states, the states associated with the electrons running around the orbital. You can also take an ion and laser cool it so that its motion can be treated quantum mechanically too. It's sort of so cold that you can add or subtract like one quantum of motion to the ion. They make very nice qubits. They have very long coherence times, sort of many seconds. We have pretty low error rates in terms of the gates that we want to do and the measurement, and we can sort of reconfigure the connection. So these are all sort of, you know, promising sort of things if you wanted to make a quantum computer out of this, but all these numbers have to be better before we're able to really get to where we want to go. These are per operation. So every time you do a single qubit gate, there's a 1 in a million chance that you messed it up. And every time you do an entangling gate, there's a 1 in 1,000 chance that you messed it up. Yeah. There's also an error from just sitting there because there's a coherence time. So if you just sit there, you will eventually slowly lose your quantum information too. But really, this is sort of like a very coherent, tunable set of states that we can run with. I don't think I want to belabor this one too long, but basically we use laser beams to basically perform the readout. So this is how we can shine laser beams that connect different energy levels to cool our ions, and to control the ions, we shine other laser beams, or we shine microwave magnetic fields. Don't worry about the details of this. It's just sort of gives you some sense. And then when you want to do readout, you shine laser beams on, and you can actually get, like you'll see, like a little glowing dot on your camera. This was in this qubit state, and that was in that qubit state. So when we talk about the meter, right, when I was talking about you couple the qubit to a meter, like effectively, this is what the meter looks like right here, right? This is the meter reading 1, and that's the meter reading 0, basically. So this is how we turn this quantum state, is with a laser beam that then turns into the ion either emitting light or not emitting light. That's how we make the meter that's measuring our qubit. How do we hold on to these things? We can actually take metal electrodes in vacuum and put radio frequency electric fields on them. And basically, you make here, at this location, what looks like a saddle. So it's sort of, in one direction, it's curved up. So an ion would sort of like not want to head up that way. But in the other direction, it's curved down. So the ion would kind of want to roll down that way, right? So you say, all right, well, how are you going to hold it in place like that? And the answer is you flap the saddle. And so you kind of flap the saddle up and down a bunch. So this particle says, okay, I'm going to start rolling downhill. But as soon as it starts getting downhill, it's like, oh, wait, no, it's an uphill now. You know, and then it says, well, I'll go this way. Now this way is downhill. Oh, no, it's uphill again. And so it basically just kind of runs around and is sort of like so confused, it's like, fine, I'll just stay here. And so this is basically, this is a hand-waving explanation of how we're able to keep these ions in one place. And you can take these things which people make in like a machine shop, and you can actually sort of unfold them onto a 2D plane. And you can have exactly the same kind of trapping, but now your electrodes are all defined on a plane. And this is nice because now you can make something like that in a clean room using the kind of technology that we use to make computer circuits, you know, where you can make very complicated, intricate sets of electrodes. So this is what the inside of our lab looks like, or one of our labs, in fact. So it's kind of giant. There's a whole bunch of lasers over here, and over there, and over there, and there's electronics all the way up to the ceiling here. And this is our computer with 6 monitors for monitoring all the different things that you want to do, along with the oscilloscopes and stuff like that. And then, you know, so this is a very complex system. Don't worry about these words down here. And then, so in this, we have a whole bunch of lasers and a whole bunch of optics. So look at this, right? Here are some lasers that we've bought, and here's all these optics. Every single thing on this table was placed there by a human being for a specific reason and aligned carefully so that it points exactly the right way. So this is, you know, it's a real labor of love. And, you know, for graduate students, you know, they do a lot of this stuff. And you know, and then this is, you know, what enables us to do all the things. This lets us do things like turning the laser pulses on and off just how we want them so we can make the quantum gates, or so we can realize the meter, right? And we have lots of different colors of lasers. We have from far out in the infrared at 1900 nanometers all the way up into the UV at 235 nanometers. So we basically have all the laser wavelengths in the visible and then outside the visible. Here are some of our laser wavelengths that we use. This green is for magnesium ions, the red is for beryllium ions, and the blue is for beryllium ions. But we don't actually use these colors. We frequency double them into the ultraviolet where you can't see them. And then those are the wavelengths that the ions actually want to talk to. And we have things like this bow tie cavity right here, which is used. This is what takes green in, and then you can't see it, but UV is coming out of this crystal here because you're shooting the green into the crystal. So there's all sorts of technology that's used in order to make the kinds of laser wavelengths and things that you want, that you need to drive these gates or do these measurements. We got a lot of electronics, so I mean, there's this whole rat's nest of cables here. There's a few action figures tucked into some of the cables as a gag. And so we've got lots of electronics. Some we buy, some we make and design and build ourselves. And these are sending all sorts of signals in at sort of Wi-Fi type frequencies and low frequencies, and they need to be very low noise, or they need to be very high stability. So there's a lot of sort of custom demanding electronics in there. We have these ultra-high vacuum systems because we're trapping these ions, right? And if you have the ion in a trap and some gas molecule from air comes around and bonks into it, then you might lose it. So we take all the air out, basically to the level where we're 15 orders of magnitude below atmospheric pressure or worse. We're basically, the limit on the vacuum pressure is that the chamber's made of steel, and steel is mostly iron, and iron is a relatively big atom. And so in the spaces between the iron atoms, hydrogen, which is very tiny, can kind of squeeze through. And so the hydrogen will slowly squeeze through all the iron atoms and come into the chamber. And that's the main reason we can't get to lower vacuum pressures. To get to lower vacuum pressures, we say, all right, we're going to go so cold that the hydrogen can't move. So we go down to 4 degrees above absolute zero, and then the hydrogen doesn't move. And now we get a really nice vacuum lifetime. And we can actually trap an ion. You can trap a single ion and hold it in your trap for weeks or months even. And like the students sometimes name the ions because it's like they stick around that long. So it's kind of amazing. And you get to be there, and you have this quantum system, and you get to check its quantumness all day long, making these pulses on it and seeing like all those weird things that we were explaining at the beginning of the lecture, like, I mean, they sound weird, but when you check what the atom says, like, that's what it's doing. It's really cool. So anyway, then there's basically the way that we think about scaling up this sort of ion traps to large scale. Don't worry about this too much, but basically think of this as Manhattan, right? And so you got a whole grid of streets, and on these streets are all these cars, and each car is an ion. And so, so the idea is like you want to take some ions and you want to do a gate on them. You drive their cars over here to, 73rd Street, and this is where the entangling gate happens, right? And then you move them around to 74th Street, and that's where they hang out when they're in memory, when they're waiting to be used for another gate that they're running in. And then when you want to hook them up to a meter, you take them uptown a little bit more, and you bring them to the readout zone, and you move there. So you're now taking all these ions. You can move them around in all these sorts of directions and perform all the quantum operations on them that you want. And you could think about making this large. You could make it sort of as big as you wanted to accommodate all those million qubits that we're going to need. We're going to have all these ions in there, right? So this is a cartoon that my co-PI Didi Leibfried made about 20 years ago. And it's actually happening. So both at NIST, we've made traps that sort of look like this, and other people have made traps that look sort of like this. And Honeywell now Quantinuum down the road is basically taken this playbook, which was really sort of started by Dave Wineland, who was my postdoc advisor here and the longtime group leader and founder of the ion storage group. This was sort of a vision that he put together 25 years ago for how can you scale up a quantum computer made of trapped ions. So anyway, so we've got these sort of traps, but this is what it looks like outside the trap. There's a trap inside here, and then here's all these hand-aligned, grad student-aligned optics, and here's a giant lens that collects the light when you're doing the meter readout, and the laser beams all go in here, and then there's not even seen here are the giant tables of lasers that we have. So what we're trying to do is now make these chips that have the electrodes for moving the ions around and actually be able to integrate the control stuff into the chips too. So here, wouldn't it be nice if we could have the laser beams come out of the chip to hit the ions instead of needing them to come in from the side? Wouldn't it be nice if we could put a photon detector right under the ions so that when it's time to see is it sending off photons or not, the meter readout, you say, all right, you look for that with just a little sensitive pixel here. And if the ion sends photons down here, click, 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 that's a meter 1. And if it doesn't, then that's a meter 0. And then you can send currents through these electrodes underneath here. And those electrodes underneath there can be used to make the superpositions and to drive the entangling gates, right? So this, you could think about doing something like this. There's no alignment. You just tile it. You sort of make a big city of this that's all fabricated in some foundry, right? It's all made on a chip where we know how to make things very complex. and say, all right, now if we make something like this where it's all integrated, now it's going to be very stable. It's going to have all these different zones. And each one of these zones, because you're just duplicating what's done here, if this one is high performance, if it has low error rates for all the gates that you're doing and for the readout that you're doing and good coherence, then so will this one, and so will that one, and so will that one. And so then you could think about maybe this goes to scale. Now, this is a huge lift, and this is a cartoon, so I want to be very honest about that. But our goal is to say, hey, people aren't doing this yet commercially because this is too sort of far in the future. So the question is, can we as NIST sort of say, hey, we're going to try and like break trail here and see what can be done. So we can do gate operations by running currents through this electrode, and I will go through this, but you can basically run entangling operations on many ions at the same time by running these currents through these electrodes. And I'm gonna zip through these things because they're sort of more technical. But the idea is that we should be able to, with these currents in electrode, make high fidelity quantum gates that you can run on many different qubits at the same time, which is kind of important if you want to do a big system. And we have a trap that looks like this. And if you zoom in on this trap that we've made at NIST, we've got these electrodes here to drive these qubit control currents in. And we can do an entangling gate with about 1 error per 1,000 gates. And this is about the state of the art for anybody doing entangling gates anywhere. So we're sort of competitive with the state of the art using this technique that we think will be able to scale up. Then you could think about, as I mentioned, all right, you've got these ions and you shine a laser on them and they fluoresce to read out. And now you've got photon detectors that are in the trap right here. And you can use those for the readout. And so we made a trap like this in the NIST clean room. And if you zoom in on it, there's that little detector, and you can put the ion above it and shoot light on it, and you get about 2% of the photons that it gives off. But we can do readout with about 1 error and about 1,000 readout attempts using this nice detector. And we think we should do an order of magnitude better with our next generation. So this is pretty cool. And then there are other groups that we're now collaborating with that are able to actually make like little optical waveguides inside chips such that you can get a laser beam to come shining up out of the chip and hit an ion that you fabricated the waveguides into the chip, and then the ion that's trapped above can be controlled with those laser beams. So this is actually sort of a real thing too. And so now we have some prototypes that are currently in the fab at our collaborators at MIT Lincoln Labs that have all of these different pieces. It's sort of the this trap. And but we're going to try seeing if we can do all the sort of basic elements of this kind of scalable vision and see how good we can make it, and then sort of try and take it from there, see what happens. So with that, I'll thank you for your attention. I'll point out that we have a large group and many people have contributed to the projects that I just listed at the end, and I'm happy to take more questions.
Questions? Comments? Yeah.
So I was wondering, like, with 2 entangled qubits, couldn't you have them like really, really, really far apart and then just transmit like data like instantly?
That is such a cool question. This is something that people thought about when they learned about entanglement, and they're like, man, that would be so cool. And there was a lot of work that people did trying to figure out how to make that work. But people have basically done the math and figured out there's not actually any way that you can transmit data. So like, think about the dice example. Let's say you did the dice example, right? You and your friend take your dice to opposite sides of the universe, like you do, and then you roll the dice.